Today we're talking about random variables and probability distributions. You guys are going to learn how to find probabilities of a random variable distribution. Okay, if anything, this is kind of like more on the applied side when it comes to probability. Okay, so some of the same skills of how to write probabilities are going to come in handy here, but you're going to be looking at it over a series of different things. Okay. So first off, a random variable is used to describe the different possible outcomes which could result from a random experiment. Okay? All right? It represents the outcomes that could be possible from a random experiment. Example, okay? If I flip 2 coins, what are my outcomes?
Tails, tails, heads, tails, heads.
Okay? I have a few different outcomes. I can either get heads for both, right? Or I could get tails for both, or I could get heads, tails, or I could get tails, heads, okay? These will be my different outcomes. This right here will be an example of describing the set or listing the different possible outcomes, okay? Random variables, they can either be discrete or continuous. Have we talked about those 2 words before?
Yes.
What does discrete mean? It can be counted, whereas continuous is measured, okay? So the example I just gave, if I flip 2 coins, is that discrete or continuous? That's discrete. Wonderful. So that means on this next page, you guys shouldn't have to write down anything because we've done that, yes? Okay, a discrete random variable, x, has a set of distinct possible values, things that can be counted, okay? It hasn't changed because I put it with a random variable after it. Okay, same thing, continuous random variables, these are things that can be measured. They can take on some interval amongst the number line, okay? So the number of defective light bulbs, that would be an example of discrete. Heights of men in the room, continuous, okay? Now for any random variable, there's a corresponding probability distribution which describes the probability that the variable will take a particular value. For any random variable, there is a corresponding probability distribution. This probability distribution describes the probabilities of each of those outcomes. And it's denoted, I had to change the font because I want you guys to make sure you saw it, as P, parentheses, capital X equals lowercase x. The capital P, you guys seen that before? What does that mean? Probability. The capital X describes your random variable, describes whatever's happening, okay? You flipping 2 coins. That would be described by the capital X. The lowercase x represents like a certain type of outcome, okay? The lowercase s represents a specific type of outcome from the list of possible outcomes, okay? So lowercase s could be an example of getting 2 heads when you flip 2 coins. So capital P represents probability. Capital X represents the random variable, whatever is happening, okay? And then the lowercase x represents just one of the outcomes that could happen out of that set. So getting 2 heads when you flip 2 coins. Every probability distribution does have a few different properties, okay? They haven't changed, though, from what we talked about when we were doing regular, like normal, basic probability. All your probabilities are going to be in between 0 and 1, okay? All your probabilities are going to be in between 0 and 1. They can equal 0. They can equal 1. If you have several different probabilities in a set, they will always add up to equal 1. Just like when we were looking at our tree diagrams, all the branches always added up to equal 1 or 100%. And then when we talk about each individual probability, we're describing the probability distribution of x. So, suppose x, this is capital X, is the number of heads obtained when 2 coins are tossed. Okay? So let's say that capital X is the number of heads obtained when 2 coins are tossed. The set of X can either be 0, 1, or 2. Okay, remember, X represents the number of heads that are obtained. So you can have no heads when you flip 2 coins. You can have 1 head when you flip 2 coins, or you can have both of them be heads if you flip 2 coins. Okay, so 0, 1, 2 represents the set of X. Does everybody understand that? That is a capital X, yes. I changed the font when I'm representing a lowercase x. Now, the probabilities that are associated with them, okay? You have 1/4 if you have no heads, 1/2 for 1 head, or 1/4 for 2 heads, okay? Because remember, the different outcomes that we can get if we flip 2 coins is heads, 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 tails, tails, heads, or tails, tails, okay? If I get 0 heads, that occurs how many times? Out of how many outcomes? 4. Hence the 1/4. If I get 1 head, that can happen how many times? Out of the 4. And that reduces down to 1/2. And then 2 heads happens 1 out of 4 times. No matter what, 1/4 plus 1/4 is what? Plus 1/2 is? Okay, so your probability distribution will always add up to equal 1. And each probability is either going to be less than 1 or greater than 0. That's the 3 properties broken down. Okay? Questions? Now, this information can be represented either in a table or in a graph. As you can see here, you're more likely to see it as a probability distribution table. You'll see it like that a lot in your homework. Okay? And they'll describe exactly what capital X represents. Again, in this case, this represents the number of heads obtained when you flip 2 coins. Lowercase x represents your different ways that can happen. No heads, 1 head, or 2 heads. And then you have your respective probabilities underneath them. Could also be represented in a graph, either a bar graph, a histogram, or a dot plot. This one is the rarest I've seen. What is there? All right. And then last but not least, before we get to an example, you have uniform, discrete, random variables. Uniform, that means everybody is 1, okay? That basically means that all of your different outcomes have the same probability. Hence the word uniform. You can still find mode and median for discrete random variables as well. And so we're going to take a look at this example to practice. A magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. Let X be the number of magazines sold to a randomly selected customer. We want to state the possible values of X, construct a probability table for X, graph the probability distribution, and then find the mode and median of X, capital X. So, what are the different... Did I leave myself space to do this? No, I didn't. Okay. What are the different possible values of X? Exactly, 1, 2, 3, 4, and 5, because this random customer could walk in one day and they could either pick up 1 magazine all the way up to 5 magazines. So capital X is going to equal 1, 2, 3, 4, 5. Our probability table, how many rows does it have? Rows go across. 2. They have 2. How many columns will it have? Actually needs to have 6, because you need to have that 1 that represents X, and then the probability of big X equals little x. Okay? Remember, big X describes the random variable. The P represents their respective probabilities, and lowercase x represents your different situations. So how many magazines could they purchase? All the way up to 5. What are their probabilities for one magazine? So that would be 0.23. What about for 2 magazines? 0.38. What about for 3 magazines? 0.21. 4. 0.13 and 5. 0.05. Okay? Simple as that. And remember, all of your probabilities should add up to equal 1. Double check. That is 61, 82, 95, and then yes, 100. Okay? So let's say that they didn't tell you how many, or what was the probability of 4 magazines. Exactly. You add all the other values and subtract from 1. Good stuff. Now let's graph this distribution. Okay? What's going to go on my x-axis? 1, 2, 3, 4, 5. And what's going to go on my y's? The decimals, yes. The probability. So this is going to be my random variable x, which represents my number of magazines. And then I have my probability. Remember, anytime you have to create it yourself, you always make sure you label your x and your y-axis along with the respective scale. It's 1, 2. And then, of course, you make your scale accordingly. My largest one is 0.3, so I'm going to go by 0.1 all the way up to 0.4. I'm making a histogram or a bar graph here. Making very much a bar graph here. Okay? Make sure that if you yourself have to make a bar graph or a histogram, you're using a ruler so you can make very nice straight lines. Yes? Thank you. Now incorporating a little bit of statistics in this. What is the mode of this distribution? Very good. Mode is 2. Remember, mode means what? Most. Okay, so the one with the largest probability. So that's 2 magazines. And then what about my median? What's the formula for median? N plus 1 divided by 2. Okay? N plus 1 divided by 2. Or we can look at it as the median is the one that falls in the probability-wise. What would that be? Like what number would represent the middle of a probability distribution? 0.5. 50%, right? Where does 50% lie? In 2. Because if you were to add 0.23 and 0.38, that would give you 61. So that means 50%, that one that's smack dab in the middle, is going to fall somewhere in that 2 range. Okay? So fall somewhere in that 2 range. Questions? So remember, median is that number that's in the middle. Okay? If you're looking at like raw data, okay? But it's still your middle 50% if you think about box and whisker, cumulative frequency, the one that's represented in the middle, okay? And right now you have basically 23% of your population of people buying magazines that only buys 1 magazine, okay? When you go to 2 magazines, when you add those 2 probabilities together, you'll get 0.61 or 61%. Your 50% tile person is in those 2s, in those 2 magazines. Good? Okay. Expectation, expected value. I think we talked about this as well. Maybe. Did we talk about expected value in this class? Okay. I get my classes mixed up. I'm doing statistics in both of them, so I'm kind of like I don't remember who I said what to. So then this is good. But expectation is basically the number of times we can expect an event to occur. The number of times we can expect an event to occur. Easiest example. If I'm a 75% free throw shooter and I shoot 100 free throws, I'm expected to make how many? Because I'm a 75% free throw shooter, right? Okay? That's what expectation, that's what expected value is. Okay? It basically takes each of your basically the number that you have and you multiply it by your probability. When you're looking at a probability distribution, like what we're going to be looking at, it's basically the sum of each one of your x values times their respective probabilities. Okay? So that's what the summation notation represents from 1 to n. So for our last example, it would have been from 1 magazine to 5 magazines. Each of those x values multiplied by their probabilities added together. Expectation is also known as the mean of the probability distribution, and it is denoted by the Greek letter mu. Did I show you that before?
Yes.
Okay. That's how it's spelled. The symbol is like a long-tailed M with a curl at the end. So using our magazine example, we're going to find the expected number of magazines bought by each customer. We're going to find the expected number of magazines bought by each customer, which means I have to take each one of my x values and multiply them by their probabilities. And then what I'm going to do with each of those products, I'm going to add them together. Okay? Can you guys do this for me, please? Tell me what my expected number of magazines bought. So what is the number? 2.39. Did you run correctly or did it stop at 9? Okay. So what does this mean? That means that on average, okay, because remember expectation also means mean means average. So on average, the number of magazines bought by customers is 2.39. Questions on probability distribution, expected value. Either one. Anytime it describes a random variable and it asks you to create a probability distribution, you'll be creating tables or using your different properties to find the respective probabilities. You could also use this for, they could give you the table instead of describing the situation. Like a lot of the problems that we did in regular probability describe the situation. You yourself had to create either a tree diagram or a Venn diagram to represent the situation. So this time they give you a table and then it works the same way. Okay? This also is seen when we're talking about games and fairness. Okay? Whether or not a game is fair or not. Okay? To be fair, that means the expected value is equal to 0. The expected value is equal to 0 if a game is said to be fair. An expected gain is basically what a player will get in return or what they'll lose every time they play a respective game. Okay? It does take into account the cost that they have to put in to play the game, if there is any cost. But a game is fair is if the expected value is 0. So we're going to look at an example of that. and then we'll look at an IB example, and then I'll give you your homework for tonight. In the game of chance, a player spins a square spinner labeled 1, 2, 3, 4. The player wins an amount of money according to the table alongside. So, if they spin this spinner and they get a 1, they win $1. 2, they get $2. 3, they get $5. And 4, they get $8. More than likely, the spinner has different size sections for 1, 2, 3, and 4. Because for 4 to be that much money, that means it probably is takes a small space of it. Okay? So, find the expected return for one spin of the spinner. Find the expected return. Keyword in this is what? Expected. Okay? Return basically means like how much, if they were to play the game, how much are they expected to win? Okay? And so we find that out by doing what? 1 times 1 plus 2 times 2 plus 3 times 5 plus 4 times 8. We can do this without our calculator. We know 1 times 1 is 1, 2 times 2 is 4, 3 times 5 is, and 4 times 8 is. Messed up. My bad. I didn't catch it. Expected value means what? You got to multiply it by their probability. You got to multiply it by their probability. So that was my mistake. That was my mistake. Okay? You multiply their winnings. Okay? You multiply their winnings by their respective probabilities. Okay? So let's erase all of these. Since we do not know each of the spinner's probabilities and things like that, we are going to have to go under the assumption that each one is equally likely. So, what are their probabilities? As a fraction is what? 1/4. Okay? So to spin a 1, spin a 2, 3, and 4. So let's multiply them and add them together. We can still do this without our calculator. Let's find our expected return. So when we multiply these, we have 1/4, 2/4, 5/4, and 8/4 for a total of what? 4. So our expected return is $4. Now it says we want to find the expected gain of a player if it costs $5 to play each game. So the expected gain of a player is determined by however much they put in to play the game and how much they're expected to get back. Okay? So gain is return, how much they can get back on the game, minus how much it costs to play the game. What is their expected gain? -1. Because they can get back $4 if they play the game, but it costs $5 to play, so their expected gain is a -$1. So, would you play this game?
No.
And why not?
Because there's a high probability that you'll lose money.
Because you're going to lose money. You're more likely to lose money than to gain money. And you guys can write that out. So we talked about probability distributions today. Remember, all your probabilities should add up to equal 1. Your probabilities are going to be between 0 and 1. Okay? Remember that notation right there is going to indicate a random variable. Okay? It can be represented as a table or as a chart, so please be aware of that as well. They could just give you the chart and just tell you what X represents, so you have to be able to go from there. Okay? We also talked about expected value, which is nothing but multiplying each of your X values by their respective probabilities. And we also talk about the game being fair. What does it mean for a game to be fair? Expected value is equal to 0. And what's another name for expected value?
Expectation.
The mean. Whoever says it, it's the mean. So if they actually find the mean, that's what they're asking for. Okay?